was working for some time on the history of geometry. Every science, every art, should have its own. It gives great pleasure, which is also instructive, to see the path which the human spirit has taken, and this kind of progression, whose intervals are at first extremely long, and afterwards naturally proceed by becoming always shorter. With so many histories of mathematics already on the shelves, to undertake to write another calls for some justification. Montmort, the first modern mathematician to think of such a project, had a clear Enlightenment aim, to display the accelerating progress of the human spirit through its discoveries. This idea, that history is the record of a progress through successive less enlightened ages up to the present, is usually called Whig history in Anglo-Saxon countries, and is not well thought of. Nevertheless, in the 18th century, even if one despaired of human progress in general, the sciences seem to present a good case for such a history, and the tradition has survived longer there than elsewhere. The first true historian of mathematics, Jean-Étienne Montucla, underlined the point by contrasting the history of mathematical discovery with that which we more usually read. Our libraries are overloaded with lengthy narratives of sieges, of battles, of revolutions. How many of our heroes are only famous for the bloodstains which they have left in their path? How few are those who have thought of presenting the picture of the progress of invention, or to follow the human spirit in its progress and development? Would such a picture be less interesting than one devoted to the bloody scenes which are endlessly produced by the ambition and the wickedness of men? It is these motives, and a taste for mathematics and learning combined, which have inspired me many years ago in my retreat to the enterprise which I have now carried out. Montucla was writing for an audience of scholars, a small one, since they had to understand the mathematics, and not many did. However, the book on which he worked so hard was justly admired. The period covered may have been long, but there was a storyline. To simplify, the difficulties which we find in the work of the Greeks have been eased by the happy genius of Descartes, and this is why progress is now so much more rapid. Later authors were more cautious if no less ambitious, the major work being the massive 4-volume history of Moritz Cantor. Since then, the audience has changed in an important way. A key document in marking the change is a letter from Simone Weil written in 1932. She was then an inexperienced philosophy teacher with extreme left sympathies, and she allowed them to influence the way in which she taught. Dear Comrade, as a reply to the inquiry you have undertaken concerning the historical method of teaching science, I can only tell you about an experiment I made this year with my class. My pupils, like most other pupils, regarded the various sciences as compilations of cut and dried knowledge, arranged in the manner indicated by the textbooks. They had no idea either of the connection between the sciences, or of the methods by which they were created. I explained to them that the sciences were not ready-made knowledge set forth in textbooks for the use of the ignorant, but knowledge acquired in the course of the ages by men who employed methods entirely different from those used to expound them in textbooks. I gave them a rapid sketch of the development of mathematics, taking as central theme the duality, continuous, discontinuous, and describing it as the attempt to deal with the continuous by means of the discontinuous, measurement itself being the first step. In the short term, the experiment was a failure. Most of her pupils failed their baccalaureate and she was sacked. In the long term, her point, that science students gain from seeing their study not in terms of textbook recipes, but in its historical context, has been freed of its Marxist associations, and has become an academic commonplace. Although Weil would certainly not welcome it, the general agreement that the addition of a historical component to the course will produce a less limited science graduate owes something to her original perception. It is some such agreement which has led to the proliferation of university courses in the history of science, and of the history of mathematics in particular. Their audience will rarely be students of history, although they are no longer confined to battles and sieges. The origins of the calculus are still too hard for them. Students of mathematics, by contrast, may find that a little history will serve them as light relief from the rigors of algebra. They may gain extra credit for showing such humanist inclinations, or they may even be required to do so. A rapid search of the internet will show a considerable number of such courses, often taught by active researchers in the field. While one is still ideally writing for the general reader, it is in the first place to students who find themselves on such courses, whether from choice or necessity, that this book is addressed. On texts, and on history. Insofar as it stands in the service of life, history stands in the service of an unhistorical power, and, thus subordinate, it can and should never become a pure science such as, for instance, mathematics is. History pertains to the living man in three respects. It pertains to him as a being who acts and strives, as a being who preserves and reveres, as a being who suffers and seeks deliverance. American History Practical Math. Studyin' hard and tryin' to pass. Chuck Berry's words seem to apply more to today's student of history, mathematics, or indeed the history of mathematics, than Nietzsche's. History pertains to her or him as a being who goes to lectures and takes exams. And naturally, where there is a course, the publisher appears on the scene to see if a textbook can be produced and marketed. Probably, the first history designed for use in teaching, and in many ways the best, was Dirk Strook's admirably short text. It is probably no accident that Strook the pioneer held to a more mainstream version of Simone Weil's far-left politics. This was followed by John Fauvel and Jeremy Gray's sourcebook, produced together with a series of short texts from the Open University. This performed the most important function, stressed in the British national curriculum for history, of foregrounding primary material and enabling students to see for themselves just how different the mathematics of others might appear. Since then, broadly, the textbooks have become longer, heavier, and more expensive. They certainly sell well. They have been produced by professional historians of mathematics, and they are exhaustive in their coverage. What then is lacking? To explain this requires some thought about what history is, and what we would like to learn from it. From this, hopefully, the aims which set this book off from its competitors will emerge. E. H. Carr devoted a short classic to the subject, which is strongly recommended as a preliminary to thinking about the history of mathematics, or of anything else. In this, he begins by making a measured but nonetheless decisive critique of the idea that history is simply the amassing of something called facts in the appropriate order. Telling the story of the brilliant Lord Acton, who never wrote any history, he comments. What had gone wrong was the belief in this untiring and unending accumulation of hard facts as the foundation of history, the belief that facts speak for themselves and that we cannot have too many facts. A belief at that time so unquestioning that few historians then thought it necessary, and some still think it unnecessary today, to ask themselves the question, what is history? If we accept for the moment Carr's dichotomy between historians who ask the question, and those who consider that the accumulation of facts is sufficient, then my contention would be that most specialist or local histories of mathematics do ask the question, and that the long, general and all-encompassing texts which the student is more likely to see do not. The works of Fowler and Knorr on the Greeks, of Yushkovich, Rashid, and Berggren on Islam, the collections of essays by Jens Heurup and Henk Boss, and many others in different ways are concerned with raising questions and arguing cases. The case of the Greeks is particularly interesting, since there are so few hard facts to go on. As a result, a number of handy speculations have acquired the status of facts, and this in itself may serve as a warning. For example, it is usually stated that Eudoxus of Cnidus invented the theory of proportions in Euclid's book V. There is evidence for this, but it is rather slender. Fowler is suspicious, and Knorr more accepting, but both, as specialists, necessarily argue about its status. In all general histories, it has acquired the status of a fact, because if history is about facts, you must have a clear line which separates them from non-facts, and speculations, reconstructions, and arguments disrupt the smoothness of the narrative. As a result, the student is not, I would contend, being offered history in Carr's sense. The distinguished authors of these 750-page texts are writing in the Acton mode, even though in their own researches their approach is quite different. Indeed, in this millennium, they can no longer write like Montucla of an uninterrupted progress from beginning to present-day perfection, and they are aware of the need to be fair to other civilizations. However, the price of this academic good manners is the loss of any argument at all. One is reminded of Nietzsche's point that it is necessary, for action, to forget, in this case, to forget some of the detail. And there are two grounds for attempting a different approach, which 1. There are a number of other useful source books, for example, by Struck, but Fauvel and Gray is justly the most used and will be constantly referred to here. 2. Ivor Grattan Guinness's recent work escapes the above categorization by being relatively light, cheap, and very strongly centered on the neglected 19th century. Although appearing to be a history of everything, it is nearer to a specialist study. Have driven me to write this book. 1. The supposed humanization of mathematical studies by including history has failed in its aim if the teaching lacks the critical elements, which should go with the study of history. 2. As the above example shows, the live field of doubt and debate, which is research in the history of mathematics, finds itself translated into a dead landscape of certainties. The most interesting aspect of history of mathematics as it is practiced is omitted. At this point you may reasonably ask what better option this book has to offer. The example of the eudoxis fact above is meant to preempt such a question by way of illustration. We have not, unfortunately, resisted the temptation to cover too wide a sweep, from Babylon in 2000 BCE to Princeton 10 years ago. We have, however, selected, leaving out Egypt, the Indian contribution aside from Kerala, and most of the European 18th and 19th centuries. Sometimes a chapter focuses on a culture, sometimes on a historical period, sometimes on a specific event or turning point. At each stage our concern will be to raise questions, to consider how the various authorities address them, perhaps to give an opinion of our own, and certainly to prompt you for one. Accordingly, the emphasis falls sometimes on history itself, and sometimes on historiography, the study of what the historians are doing. Has the Islamic contribution to mathematics been undervalued, and if so, why? And how should it be described? Was there a revolution in mathematics in the 17th century, or at any other time, for that matter? By what criteria would one decide that one has taken place? Such questions are asked in this book, and the answers of some writers with opinions on the subjects are reported. Your own answers are up to you. Nota sethatoire not offering an alternative ethos works of scholarship which we recommend. Unlike the text cited above, this book does not set out to argue a case. The intention is to send you in search of those who have presented the arguments. Often lack of time or the limitations of university libraries will make this difficult, if not impossible, in French and long out of print. In any case, the reference and, hopefully, a fair summary of the argument will be found here. This approach is reflected in the structure of the chapters. In each, an opening section sets the scene and raises the main issues which seem to be important. In most, the following section, called Literature, discusses the sources for the period, with some remarks on how easy they may be to locate. Given the poverty of many libraries, it would be good to recommend the internet. However, you will rarely find anything substantial, apart from Euclid's elements, and you will, as always with internet sources, have to wade through a great mass of unsupported assertions before arriving at reliable information. The St. Andrews does have almost all the biographies you might want, with references to further reading. If your library has any money to spare, you should encourage it to invest in the main books and journals, but if you could do that, this book might even become redundant. 3. And if key texts like Qin Zhouxiao's Zhouzheng Shushu and Al-K-Ashai's Calculator's Key were translated into English. Examples. For a long time I had a strong desire in studying and research in sciences to distinguish some from others, particularly the book Elements of Geometry, which is the origin of all mathematics, and discusses point, line, surface, angle, etc. At the age of 11, I began Euclid, with my brother as my tutor. This was one of the great events of my life, as dazzling as first love. I had not imagined there was anything so delicious in the world. From that moment until I was 38, mathematics was my chief interest and my chief source of happiness. Perhaps the central problem of the history of mathematics is that the texts we confront are at once strange and familiar. If we read Aristotle on how stones move, or on how one should treat slaves, it is clear that he belongs to a different time and place. If we read Euclid on rectangles, we may be less certain. Indeed, one could fill a whole chapter with examples taken from the Elements, the most famous textbook we have and one of the most enigmatic. Because our history likes to center itself on discoveries, it is common to analyze the ingenious but hypothetical discoveries which underlie this text, rather than the text itself. And yet the student can learn a great deal simply by considering the unusual nature of the document and asking some questions. Take Proposition 2.1. If there are two straight lines, and one of them is cut into any number of segments whatever, then the rectangle contained by the two straight lines equals the sum of the rectangles contained by the uncut straight line and each of the segments. Let A and BC be two straight lines, and let BC be cut at random at the points D and E. I say that the rectangle A by BC equals the sum of the rectangle A by BD, the rectangle A by DE, and the rectangle A by EC. If we draw the picture, we see that Euclid is saying in our terms that A equals Ax plus I plus AZ, what in algebra is called the distributive law. Some commentators would say that that is, essentially, what he is saying. Others would say that it is important that he is using a geometric language, not a language of number. Such differences were expressed in a major controversy of the 1970s, which you will find in Fauvel and Gray section 3. Whichever point of view we take, we can ask why the proposition is expressed in these terms, and how it might have been understood by a Greek of Euclid's time, thought to be about 300 BCE, and by one of his readers at any time between then and the present. Euclid's own views on the subject are unavailable and are therefore open to argument. And the question of what statements like Proposition 2.1 might mean is given a particular weight by 1. The poverty of source material, almost no writings from before Euclid's time survive. 2. The central place which Greek geometry holds in the Islamic Western tradition. Figure 1. The figure for Euclid's Proposition 2.1. A second well-known example, equally interesting, confronted the Greeks in the 19th century. A classical problem dealt with by the Greeks from the 5th century onwards was the doubling of the cube, given a cube C, to construct a cube D of double the volume. Clearly this amounts to multiplying the side of C by 2. A number of constructions for doing this were developed, even perhaps for practical reasons. As we shall discuss later, while Greek writers seem to distinguish solutions which they thought better or worse for particular reasons, they never seem to have thought the problem insoluble. It was simply a question of which means you chose. A much later understanding of the Greek tradition led to the imposition of a rule that the construction should beden with ruleran compassisonly. These excluded all the previous solutions, and in the 19th century following Galois' work on equations, it was shown that the ruleran compass solution was impossible. We can therefore see 3 stages. 1. A Greek tradition in which a variety of methods are allowed, and solutions are found. 2. An interpreted Greek tradition in which the question is framed as a ruler and compass problem, and there is a fruitless search for a solution in these restricted terms. 3. An algebraic stage in which attention focuses on proving the impossibility of the interpreted problem. All 3 stages are concerned with the same problem, one might say, but at each stage the game changes. Are we doing the same mathematics or a different mathematics? In studying the history, should we study all 3 stages together, or relate each to its own mathematical culture? Different historians will give different answers to these questions, depending on what one might call their philosophy. To think about these answers and the views which inform them is as important as the plain telling of the story. Historicism and presentism. Littlewood said to me once, "Are not clever schoolboys or its scholarship candidates, but as fellows of another college." There is not, and cannot be, number as such. We find an Indian, an Arabian, a classical, a Western type of mathematical thought and, corresponding with each, a type of number, each type fundamentally peculiar and unique, an expression of a specific world feeling. A symbol having a specific validity which is even capable of scientific definition. A principle of ordering the become which reflects the central essence of one and only one soul, viz. the soul of that particular culture. In the rest of this introduction we raise some of the general problems and controversies, which concern those who write about the history of science, and mathematics in particular. Following on from the last section in which we considered how far the mathematics of the past could be updated, it is natural to consider 2 approaches to this question, historicism and what is called presentism. They are not exactly opposites, A glance at the reviews in ISIS will show that while historicism is sometimes considered good, presentism, like a Whig history, is almost always bad. It is hard to be precise in definition, since both terms are widely applied. Briefly, historicism asserts that the works of the past can only be interpreted in the context of a past culture, while presentism tries to relate it to our own. We see presentism in Hardy and Littlewood's belief that the ancient Greeks were Cambridge men at heart. By contrast, Spengler, today a deeply unfashionable thinker, shows a radical historicism in going so far as to claim that different cultures have different concepts of number. It is unfair, as we shall see, to use him as representative. Almost no one would make such sweeping claims as he did. The origins of the history of mathematics, as outlined above, imply that it was at its outset presentist. An Enlightenment viewpoint such as that of Montucla saw Archimedes as engaged on the same problems as the moderns. He was simply held back in his efforts by not having the language of Newton and Descartes. Classical historicism of the 19th century German school arose in reaction to such a viewpoint, often stressing hermeneutics, the interpretation of texts in relation to what we know of their time of production. Because it was generally applied to religious or literary texts, it was not seen as leading to the radical relativism which Spengler briefly made popular in the 1920s. To assert that a text must be studied in relation to its time and culture is not necessarily to say that its soul is completely different from our own. Indeed, if it were, it is hard to see how we could hope to understand it. Schleiermacher in the early 19th century set out the project in ambitious terms. The vocabulary and the history of an author's age together form a whole from which his writings must be understood as a part. And we shall find such attempts to understand the part from the whole, for example, in Netz's study of Greek mathematical practice, or Martzloff's attempt to understand the ancient Chinese texts. The particular problem for mathematics, already sketched in the last section, is its apparent timelessness, the possibility of translating any writing from the past into our own terms. This makes it apparently legitimate to be unashamedly presentist and consider past writing with no reference to its context, as if it were written by a contemporary, a procedure which does not really work in literature, or even in other sciences. To take an example, a Babylonian tablet of about 1800 BCE may tell us that the side of a square and its area add to 45, by which it means 4,560 is equal to 3. There may follow a recipe for solving the problem and arriving at the answer 30 for the side of the square. Clearly we can interpret this by saying that the scribe is solving the quadratic equation x plus x equals. In a sense this would be absurd. Of equations, quadratic or other, the Babylonians knew nothing. They operated in a framework where one solved particular types of problems according to certain rules of procedure. The tablet says in these terms, here is your problem. Do this, and you arrive at the answer. A historicist approach sees Babylonian mathematics as framed in these terms. You can find it in Heurup or Ritter. However, the simple dismissal of the translation as unhistorical is complicated by 2 points. The first is straightforward, that it can be done and makes sense, and that it may even help our understanding to do so. The second is that it seems that there could be a transmission line across the millennia which connects the Babylonian practice to the algebra of Al-Khwarizmi in the 9th century CE. In the latter case we seem to be much more justified in talking about equations. What has changed, and when? A presentist might. For, Heurup is even dubious about the terms add and a square in the standard translation of such texts, claiming that neither is a correct interpretation of how the Babylonians saw their procedures. Argue that, since Babylonian mathematics has become absorbed into our own, it makes sense to understand it in our own terms. The problem with this idea of translation, however, is that it is a dictionary which works one way only. We can translate Archimedes' results on volumes of spheres and cylinders into our usual formulae, granted. However, could we then imagine explaining the arguments, using calculus, by which we now prove them to Archimedes? At some point the idea that he is a fellow of a different college does seem to come up against a difference between what mathematics meant for the Greeks and what it means for us. As with the other issues raised in this introduction, the intention here is not to come down on one side of the dispute, but to clarify the issues. You can then observe the arguments played out between historians, and make up your own mind. Revolutions, paradigms, and all that. Though most historians and philosophers of science would disagree with some of the details of Kuhn's 1962 analysis, it is, I think, fair to say that Kuhn's overall picture of the growth of science as consisting of non-revolutionary periods, interrupted by the occasional revolution, has become generally accepted. From Kuhn's sociological point of view, astrology would then be socially recognized as a science. This would, in my opinion, be only a minor disaster. The major disaster would be the replacement of a rational criterion of science by a sociological one. If we grant that the subject of mathematics does change, how does it change, and why? This brings us to Thomas Kuhn's short book The Structure of Scientific Revolutions, a text which has been fortunate, even if its author has not. Quite unexpectedly, it seems to have appealed to the zeitgeist, presenting a new and challenging image of what happens in the history of science, in a way which is simple to remember, persuasively argued, and very readable. Like Newton's laws of motion, its theses are few enough and clear enough to be learned by the most simple-minded student. Briefly, they reduce to 4 ideas. Normal science. Most scientific research is of this kind, which Kuhn calls a puzzle solving. It is carried out by a community of scholars who are in agreement with the framework of research. Paradigm. This is the collection of allowable questions and rules for arriving at answers within the activity of normal science. What force might move the planets was not an allowable question in Aristotelian physics. It became one with Galileo and Kepler. Revolutions. From time to time, in Kuhn's preferred examples, when there is a crisis which the paradigm is unable to deal with by common agreement, the paradigm changes. A new community of scholars not only change their views about their science, but change the kinds of questions and answers they allow. This change of the paradigm is a scientific revolution. Examples include physics in the 16th-17th century, chemistry around 1800, relativity and quantum theory in the early 20th century. Incommensurability. After a revolution, the practitioners of the new science are again practicing normal science, solving puzzles in the new paradigm. They are unable to communicate with their pre-revolutionary colleagues, since they are talking about different objects. Consider the men who called Copernicus mad because he proclaimed that the Earth moved. They were not either just wrong or quite wrong. Part of what they meant by Earth was fixed position. Their Earth, at least, could not be moved. Setting aside for the moment the key question of whether any of this might apply to mathematics, its conclusions have aroused strong reactions. Popper, as the quote above indicates, was prepared to use the words major disaster, and many of the so-called science warriors of the 1990s saw Kuhn's use of incommensurability in particular as opening the floodgates to so-called relativism. For if, as Kuhn argued in detail, there could be no agreement across the divide marked by a revolution, then was one science right and the other wrong, or, and this was the major charge, was one indifferent about which was right. Relativism is still a very dangerous charge. And the idea that he might have been responsible for encouraging it made Kuhn deeply unhappy. Consequently, he spent much of his subsequent career trying to retreat from what some had taken to be evident consequences of his book. I believe it would be easy to design a set of criteria, including maximum accuracy of predictions, degree of specialization, number of concrete problem solutions, which would enable any observer involved with neither theory to tell which was the older, which the descendant. For me, therefore, scientific development is, like biological development, unidirectional and irreversible. One scientific theory is not as good as another for doing what scientists normally do. In that sense, I am not a relativist. It is often said that writers have no control over the use to which readers put their books, and this seems to have been very much the case with Kuhn. The simplicity of his theses and the arguments with which he backed them up, supported by detailed historical examples, have continued to win readers. It may be that the key terms normal science and paradigm, under the critical microscope, are not as clear as they appear at first reading, and many readers subscribe to some of the main theses while holding reservations about others. Nonetheless, as Gillies proclaimed in our opening quote, the broad outlines have almost become an orthodoxy, a successful, grand narrative in an age which supposedly dislikes them. So what of mathematics? It is easy to perceive it as normal science. If one makes a sociological study of mathematical research communities present or past, but has it known crisis, revolution, incommensurability even? This is the question which Gillies' collection attempted to answer. Starting from an emphatic denial by Michael Crow. His interesting, if variable, 10 theses on approaching the history of mathematics conclude with number 10, the blunt assertion. Revolutions never occur in mathematics. The argument for this, as Mertens points out in his contribution to the volume, is not a strong one. Crow aligns himself with a very traditional view, citing Henkel in 1869. In most sciences, one generation tears down what another has built. In mathematics alone, each generation builds a new story to the old structure. Other sciences may have to face the problems of paradigm change and incommensurability, but ours does not. It seems rather complacent as a standpoint, but there is some evidence. One test case appealed to by both Crow and Mertens is that of the overthrow of Euclidean geometry in the 19th century with the discovery of non-Euclidean geometries. The point made by Crow is that unlike Newtonian physics, which Kuhn persuasively argued could not be 5. This refers to a series of arguments, mainly in the United States, about the supposed attack on science by postmodernists, sociologists, feminists, and others. C. Seen as a truth in the same sense after Einstein, Euclidean geometry is still valid, even if its status is now that of one acceptable geometry among many. This point, of course, links to those raised in the previous sections. How far is Euclid's geometry the same as our own? An interesting related variant on the revolution theme, which concerns the same question, is the status of geometry as a subject. Again in Chapter 8, we shall see that geometry in the time of Euclid was an abstract study, which was marked off from the study of the world in that geometric lines were unbounded, while space was finite. By the time of Newton, space had become infinite, and geometry was much more closely linked to what the world was like. Hence, the stakes were higher, in that there could clearly only be one world and one geometry of it. The status of Euclidean geometry as one among many, to which Crow refers, is the outcome of yet another change in mathematics, later than the invention of the non-Euclidean geometries, the rise of the axiomatic viewpoint at the end of the 19th century, and the idea that mathematics studied not the world, but axiom systems and their consequences. It may be that neither of these radical changes in the role of geometry altered the truth claims of the Euclidean model. Nonetheless, there is a case for claiming that they had a serious effect on what geometry was about, and so could be treated as paradigm shifts. Indeed, we shall see early 19th century writers treating geometry as an applied science, in which case, one imagines, the Kuhnian model would be applicable. As can be seen, to some extent the debate relates to questions raised earlier, in particular how far one adheres to a progressive or a cumulative view of the past of mathematics. There have been subsequent contributions to the debate in the years since Gillies' book, but there is not yet a consensus even at the level that exists for Kuhn's thesis. External versus internal. Mathematics, under the tremendous pressure of social forces, increased not only in volume and profundity, but also rose rapidly to a position of honor. I would give a chocolate mint to whoever could explain to me why the social background of the small German courts of the 18th century, where Gauss lived, should inevitably lead him to deal with the construction of the 17-sided regular polygon. An old, and perhaps unnecessary dispute has opposed those who in history of science consider that the development of science can be considered as a logical deduction in isolation from the demands of society, and those who claim that the development is at some level shaped by its social background. Until about 30 years ago, Marxism and various derivatives were the main proponents of the external viewpoint, and the young Dirk Struck, writing in the 1930s, gives a strong defense of this position. Already at that point Struck is too good a historian not to be nuanced about the relations between the class struggle and mathematical renewal under Descartes. In interaction between theory and practice, between the social necessity to get results and the love of science for science's sake, between work on paper and work on ships and in fields, we see an example of the dialectics of reality, a simple illustration of the unity of opposites, and the interpenetration of polar forms. The history and the structure of mathematics provide example after example for the study of materialist dialectics. The extreme disfavor under which Marxism has fallen since the 1930s has led those who believe in some influence of society to abandon classes and draw on more acceptable concepts such as milieus, groups, and actors, and Dieudonné has died without conceding that anyone had earned his chocolate mint. Yet in a sense the struggle has sharpened, under the influence of what has been called the Edinburgh School or the strong program in the sociology of knowledge, originally propounded in the 1980s by Barry Barnes and David Bloor. For Marxists believed that scientific knowledge was objective, and hence the rising classes would be inspired to find out true facts, as Mao famously said. Where do correct ideas come from? Do they fall from the sky? No. Are they innate in the mind? No. They come from social practice, and from it alone. They come from three kinds of social practice: the struggle for production, the class struggle, and scientific experiment. Notice that Mao too allows for internal factors, the use of scientific experiment to arrive at correct ideas. The Edinburgh School has led the way in an increased skepticism, even relativism on the issue of scientific truth, and in seeing, in the limit, all knowledge as socially determined. In one way such a view might be easier for mathematicians to accept than for physicists, since the latter consider it important for their justification that electrons, quarks, and so on should be objects out there, rather than social constructions. Mathematicians, one would think, are less likely to feel the same way about the square root of -1, however useful it may be in electrical engineering. In this respect, Leopold Kronecker's famous saying that God made the natural numbers, all else is the work of man, places him as a social constructivist before his time. A deliberately hard test case in a recent text by some of the school goes to work on the deduction of 2 + 2 = 4, on proof in general, underlying assumptions, logical steps in proof, and so on. So-called self-evidence is historically variable. Rather than endorsing one of the claims to self-evidence and rejecting the other, the historian can take seriously the unprovability of the claims that are made at this level, and search out the immediate causes of the credibility that is attached or withheld from them. Self-evidence should be treated as an actor's category. Because they are sociologists rather than historians, the Edinburgh School tend not to have an underlying theory of historical change, hence they are stronger on identifying difference across cultures or periods than on identifying the basis on which change takes place. While influenced by Kuhn, and so seeing some sort of a crisis or breakdown in the consensus as motivating, they feel that the actors and their social norms must have something to do with it. However, the society in crisis may be simply the mathematical research community, in which case we are still in a modified internal a model similar to that of Kuhn, or it may be influenced by the wider community, as in the case of Joan Richard's study of the relation between Euclidean geometry and the Victorian established church. As Paul Forman, responsible for one of the best studies of the interaction of science and society, has pointed out recently, the accusation of relativism seems to have driven many advocates of the strong program into a partial retreat from a position, which was never very historically explicit. And yet, the hardline internalist position is still considered inadequate by many historians, even if they are not sure what mixture of determinants they should put in its place. Often in the last 2 centuries, internal determinants seem paramount, though in operational research, computing. 6. One could, for example, point out that knot theory, while first developed in the 1870s by an electrical engineer to deal with a physical problem, has proceeded according to an apparent internal logic of its own since then. See Chapter 9. And even chaos theory 1 could see outside forces at work. In earlier history, when we have the evidence, it often seems the other way round. In his commentary on the rectangular arrays section of the 9 chapters, Liu Hui analyses a problem on different grades of patty. He says, it is difficult to comprehend in mere words, so we simply use patty to clarify. Does he mean that the authors of the classical text first hit on the idea of using matrix algebra, and then applied it to grades of Paddy for ease of exposition? We have no evidence, but it seems easier to believe that the discovery went the other way round, from problems about Paddy to matrices. It is easy to say that among most responsible historians now the tendency is to take both internal and external determinants seriously in any given situation and to give them their appropriate weight. The problem is that with the eclipse of Marxism and with doubts about Kuhn's relevance to mathematics, there is no very well-organized version of either available to the historian. We shall continue to appeal to Marxism where we find either of them relevant in what follows. Eurocentrism. I propose to show that the standard treatment of the history of non-European mathematics exhibits a deep-rooted historiographical bias in the selection and interpretation of facts, and that mathematical activity outside Europe has in consequence been ignored, devalued, or distorted. His willingness to concoct historically insupportable myths that are pleasing to his political sensibilities is obvious on every page. His eagerness to insinuate himself into the good graces of the supposed educators who incessantly preach the virtues of multiculturalism and the vices of a Eurocentrism is palpable and pervasive. Review on. It would appear that the argument set out by Joseph has not been won yet. I have no way of judging the book under review in the second quote, but there is an underlying suggestion that the reviewer has heard more than enough about Eurocentrism and is pleased to find a book which is both anti-Eurocentrist and intellectually shoddy, thereby supporting his or her suspicions. This is the fashionable nonsense school of reviewing, and it is not going to go away. In fact, the current anti-Islamic trend in the West, and specifically in the United States, may lend it more support. What is Eurocentrism? In general terms, it is the privileging of European American discourse over others, most often African or Asian, in history. It might mean privileging the European account of the Crusades, or of the Opium Wars, or any imperialist episode over the other side. For what it might mean in mathematics, we should go back to Joseph who, at the time he began his project, had a strong, passionate, and undeniable point. If we count as the European tradition one which consists solely of the ancient Greeks and the modern Europeans, and we shall soon see how problematic that is, a glance through many major texts in the history of mathematics showed either ignorance or undervaluing of the achievements of those outside that tradition. We shall discuss this in more detail later, but his book was important. It is the only book in the history of mathematics written from a strong personal conviction, and it is valuable for that reason alone. It also stands as the single most influential work in changing attitudes to non-European mathematics. The sources, such as Neugebauer on the 7. The title of a book which is devoted to attacking what it sees as sloppy thinking about science by postmodernists, feminists, postcolonialists, and many others. Egyptians and Babylonians, or Yashkovich on the Islamic tradition, may have been available for some time before, but Joseph drew their findings into a forceful argument which, since its main thrust is easy to follow, has made many converts. After sketching the views which he intends to counter, Joseph characterizes three historical models which can be used to describe the transmission of mathematical knowledge. First, the classical Eurocentric trajectory, already referred to. Mathematics passed directly from the ancient Greeks to the Renaissance Europeans. Second, the modified Eurocentric trajectory. Greece drew to some extent on the mathematics of Egypt and Babylonia, while after Greek learning had come to an end, it was preserved in the Islamic world to be reintroduced at the Renaissance. Third, Joseph's own alternative trajectory. This, with a great many arrows in the transmission diagram, stresses the central role of the Islamic world in the Middle Ages as a cultural center in touch with the learning of India, China, and Europe, and acting both as transmitter and receiver of knowledge. The more we know, particularly of the Islamic world, the more this appears to be a reasonably accurate picture, and while Joseph's tone can be polemical and some of his detailed points have been questioned, his arguments are rarely overstated. We are learning more of the mathematics of India, China, and Islam, as of the Greeks' predecessors, and scholars are becoming better able to read their texts and understand their way of thinking about mathematics. The body of the book is given over to a detailed account of the various non-European cultures and their contributions. Interestingly, his account is now to be found substantially unchanged in most of the standard textbooks. The culture warriors may rage against fashionable anti-Eurocentrism, but as far as mainstream teaching of the history of mathematics is concerned, it seems to have been absorbed successfully. Again, we shall return to this point later. The specific reasons for Eurocentrism in the history of mathematics have been twofold. The first is the very high value accorded to the work of the ancient Greeks specifically, the second the emphasis on discovery and proof of results. These are indeed linked. Much of the Greek work was organized in the form of result plus proof. All the same, there is an important point to be made here, namely, that after the Greeks it was the Arabs who continued the tradition, with propositions and proofs in the Euclidean mode. If we contrast Islamic mathematics of around 1200 with that of Western Europe, we would have no doubt that the former was, in our terms, Western, and the latter a primitive outsider. However, this has not, until recently, helped the integration of the great Islamic mathematicians into the Western tradition, and if it did, it would still leave the Indians and Chinese, with very different practices, outside it. Indeed, the problem of Eurocentrism could be seen in Cuneiform terms as one of paradigms. The Greek paradigm, or a version of it, is one which has in some form persisted into modern Western mathematics and hence traditional histories, have constructed themselves around that paradigm, either leaving out or subordinating ways of doing mathematics which did not fit. It is only more recently that a more culturally aware history has been able to ask how other cultures thought of the practice of mathematics, and to escape the trap of evaluating it against a supposed Greek or Western ideal. 8. Not at all times, Descartes, Newton in his early work, and Leibniz initiated a tradition in which the Euclidean mode was at least temporarily abandoned. See chapters 6 and 7. 1. Babylonian Mathematics. 1. On Beginnings. Obviously, the pioneers and masters of hydraulic society were singularly well equipped to lay the foundations for two major and interrelated sciences, astronomy and mathematics. Based on intensive cereal agriculture and large-scale breeding of small livestock, all in the hands of a centralized power, was quickly caught up in a widespread economy which made necessary the meticulous control of infinite movements, infinitely complicated, of the goods produced and circulated. It was to accomplish this task that writing developed. Indeed, for several centuries, this was virtually its only use. When did mathematics begin? Naive questions like this have their place in history. The answer is usually a counter-question. In this case, what do you mean by mathematics? A now rather outdated view restricts it to the logical deductive tradition inherited from the Greeks, whose beginnings are discussed in the next chapter. The problem then is that much interesting work which we would commonly call a mathematics is excluded, from the Leibnizian calculus to the kind of exploratory work with computers and fractals, which is now popular in studying complex systems and chaotic behavior. Many cultures before and since the Greeks have used mathematical operations from simple counting and measuring onwards, and solved problems of differing degrees of difficulty. The question is how one draws the line to demarcate when mathematics proper started, or if indeed it is worth drawing. As we shall see, the early history of Greek mathematics is hard to reconstruct with certainty. In contrast, the history of the much more ancient civilizations of Iraq in the years from 2500 to 1500 BCE provides a quite detailed, if still patchy record of different stages along a route which leads to mathematics of a kind. Without retracing the whole history in detail, in this chapter we can look at some of these stages as illustrations of the problem raised by our initial questions. Mathematics of what kind, and what for? And what are the conditions which seem to have favored its development? Before attempting to answer any of these questions, we need some minimal historical background. Various civilizations, with different names, followed each other in the region which is now Iraq, from about 4000 to 300 BCE. Our evidence about them is entirely archaeological, the artifacts and records which they left, and which have been excavated and studied by scholars. From a very early date, for whatever reason, they had, as the quotation from Botero describes, developed a high degree of hierarchy, slave or semi-slave labor, and obsessive bureaucracy, in the service of a combination of kings, gods, and 1. This relates to the questions raised recently in the field of ethnomathematics if mathematical practices used, often without explicit description or justification, in a variety of societies for differing practical ends from divination to design. For these see, for example, Asher, because the subject is mainly concerned with contemporary societies, it will not be discussed in this book. Their priests. Writing of the most basic kind was developed around 3300 BCE, and continued using a more developed form of the original cuneiform script for 3,000 years, in different languages. The documents have been unusually well preserved because the texts were produced by making impressions on clay tablets, which hardened quickly and were preserved even when thrown away or used as rubble to fill walls. A relatively short period in the long history has provided the main mathematical documents, as far as our present knowledge goes. As usual, we should be careful. Our knowledge and estimation of the field has changed over the past 30 years, and we have no way of knowing what future excavation or decipherment will turn up and what texts, currently ignored, will be found important by future researchers. In this period, from 2500 to 1750 BCE, the Sumerians, founders of a South Iraqi civilization based on Uruk, and inventors of writing among other things, were overthrown by a Semitic-speaking people, the Akkadians, who as invaders often do, adopted the Sumerian model of the state and used Sumerian as the language of culture. A rough guide will show the periods from which our main information on mathematics derives. 2500 BCE, Farah period. The earliest school texts, from Farah near Uruk, beginning of phonetic writing. 2340 BCE, Akkadian dynasty. Unification of all Mesopotamia under Sargon. Cuneiform is adapted to write in Akkadian, number system further developed. 2100 BCE, Ur-3. Re-establishment of Ur, an ancient Sumerian city, as capital. Population now mixed, with Akkadians in the majority. High point of bureaucracy under King Solji. 1800 BCE, Old Babylonian, or OB. Supremacy of the northern city of Babylon under Hammurabi and his dynasty. The most sophisticated mathematical texts. MS 1844. Figure 1, a mathematical tablet. Figure 2, tablet VAT 16773, numerical tally of different types of pigs. Each dynasty lasted roughly 100 years and was overthrown by outsiders, following a common pattern, so you should think of less centralized intervals coming between the periods listed above. However, there was a basic continuity to life in southern Iraq, with agriculture and its bureaucratic priestly control probably continuing without much change throughout the period. In the quotation citat the beginning of the chapter, their renegade Marxist Karl Wittfogel advanced the thesis that mathematics was born out of the need of the ancient Oriental states of Egypt and Iraq to control their irrigation. In Wittfogel's version, this hydraulic project was indeed responsible for the whole of culture from the formation of the state to the invention of writing. The thesis has been attacked over a long period, and now does not stand much scrutiny in detail, but a residue which bears examining is that the ancient states of Egypt and Iraq had a broadly similar priestly bureaucratic structure, and evolved both writing and mathematics very early to serve bureaucratic ends. Indeed, as far as our evidence goes, mathematics precedes writing, in that the earliest documents are inventories of goods. The development of counting symbols seems to take place at a time when the things counted are described by pictures, rather than any phonetic system of writing. The bureaucracy needed accountancy before it needed literature, which is not necessarily a reason for mathematicians to feel superior. On this basis, there could be a case for considering the questions raised above with reference to ancient Egypt as well. The organization of Egyptian society and its use of basic mathematical procedures for social control were similar, if slightly later. However, the sources are much. 2. There were certainly early poems celebrating heroic actions, the Gilgamesh being particularly famous. But in many societies, such poems are not committed to writing, and this seems to have been the case with the Gilgamesh for a long time, before it too was pressed into service by the bureaucracy to be learned by heart in schools. Poorer, largely because papyrus, the Egyptian writing material, lasts so badly. There are 2 major mathematical papyri and a handful of minor ones from ancient Egypt. It is also traditional to consider Babylonian mathematics more serious than Egyptian, in that its number system was more sophisticated, and the problems solved more difficult. This controversy will be set aside in what follows. Fortunately, the re-evaluations of the Babylonian work which we shall discuss below make it outdated. The Iraqi tradition is the earliest, it is increasingly well known, discussed, and argued about, and on this basis we can restrict attention to it. 2 Sources and selections. Even with great experience, a text cannot be correctly copied without an understanding of its contents. It requires years of work before a small group of a few hundred tablets is adequately published. And no publication is final. We need to establish the economic and technical basis which determined the development of Sumerian and Babylonian applied mathematics. This mathematics, as we can see today, was more one of a bookkeepers and a traders than one of a technicians and engineers. Above all, we need to research not simply the mathematical texts, but also the mathematical content of economic sources systematically. The quotations above illustrate how the study of ancient mathematics has developed. In the first place, crucially, there would not be such a study at all if a dedicated group of scholars, of whom Neugebauer was the best known and most articulate, had not devoted themselves to discovering mathematical writings, to deciphering their peculiar language, their codes, and conventions, and to trying to form a coherent picture of the whole activity of mathematics as illustrated by their material. Overwhelmingly, exercise and tables said by scribes and obscules. These pioneers played a major role in undermining a central tenet of Eurocentrism, the belief that serious mathematics began with the Greeks. They pictured a relatively unified activity, practiced over a short period, with some interesting often difficult problems. However, it is the fate of pioneers that the next generation discovers something which they had neglected. And Veyman, as a Soviet Marxist, was in a particularly good position to realize that the neglected mathematics of bookkeepers and traders was needed to complete the rather restricted picture derived from the scribal schools. For various reasons, its simplicity, based on a small body of evidence, and its supposed greater mathematical interest, the older picture is easy to explain and to teach, and you will find that most accounts of ancient Iraqi mathematics concentrate on the work of the OB school tradition. In this chapter, trying to do justice to the older work and the new, we shall begin by presenting what is known of the classical period of mathematics, and then consider how the picture changes with the new information which we have on it and on its more practical predecessors. At the outset, and this is implicit in what Neugebauer says, we have to face the problem of reading texts. The ideal of a history in the critical liberal tradition, such as this aims to be, is that on any question the reader should be pointed towards the main primary sources, the main interpretations and their points of disagreement, and perhaps a personal evaluation. The reader is then encouraged to think about the questions raised, form an opinion, and justify it with reference to the source material. Was it possible to be an atheist in the 16th century, when was non-Euclidean geometry discovered, and by whom? There is plenty of material to support. Figure 3. The Stonewaying Tablet YBC 4652, Photograph and Line Drawing. Arguments on such questions, and there are writers who have used the material to develop a case. When we approach Babylonian mathematics, we find that this model does not work. There are, it is true, a large number of documents. They are partly preserved, sometimes reconstructed clay tablets, written in a dead language, Sumerian or Akkadian or a mixture, using the Cuneiform script. It should also be noted that their survival is a matter of chance, and that we have few ways of knowing whether the selection which we have is representative. There seem to be gaps in the record, and most of our studies naturally are directed at the periods from which most evidence has survived. Unless we want to spend years acquiring specialist knowledge, we must necessarily depend on experts to tell us how to read the tablets, to decipher the script, and to translate the language. It is useful to begin with an example. The tablet pictured is called YBC 4652. Here is the text of lines 4, 6, which is cited in Fauvel and Gray as 1E.1. The language is Akkadian, the date about 1800 BCE. Na ipa kila nunatag 8 by ila 3 jin baida. Magi U3 gal EG U13 gal ARA 21 tab bida. Ma. Ila 1 mana sag na 4 and nam sag na 4 412 jin. Note that the figures in this quotation correspond to Babylonian numerals, of which more will follow later, that is, where in the translation below the phrase 1/13 appears, a more accurate translation would be 13 fraction, which shows that the word 13 is not used. There is a special sign for. The translation reads as follows. I found a stone, did not weigh it, I weighed 8 times its weight, added 3 jin 1/3 of 1/13 I multiplied by 21, added, and then. I weighed 1 mana. What was the origin of the stone? The origin of the stone was 412 jin. 3. Except for this 4 in ana, which seems to be a reference to the meaning of ana we are dealing with. As you can see, from tablet to drawing to written Akkadian text to translation, we have stages over which you and I have no control. We must make the best of it. There are subsidiary problems. For example, we need to accept a dating on which there is general agreement, but whose basis is complicated. If a source gives the dates of King Uarnamu of the 3rd dynasty as about 2111, 2095 BCE, where do these figures come from, and what is the force of about? Most scholars are ready to give details of all stages, but we are in no position to check. The restricted range of the earlier work perhaps made a consensus easier. In the last 30 years, divergent views have appeared. Even the traditional interpretation of the OB mathematical language has been questioned. An excellent account of this history is given by Hoyrup. In general, the present-day historians of mathematics in ancient Iraq are models of what a secondary source should be for the student. They discuss their methods, argue, and reflect on them. But given the problems of script and language we have referred to, when experts do pronounce, by interpreting a document as a theoretical calculation of cattle yields, for example, rather than an actual count, the reader can hardly disagree, however odd the idea of doing such a calculation in ancient UR may seem. On a core of OB mathematics there is a consensus, which dates back to the pioneering work of Neugebauer and Thoreau-Daingen in the first half of the 20th century. There may be an argument about whether it is appropriate to use the word add in a translation, but in the last instance there is agreement that things are being added. This is helpful, because it does give us a coherent and reliable picture of a practice of mathematics in a society about which a good deal is known. However, it is necessarily restricted in scope, and the sources which are usually available do not always make that fact clear. For example, most texts which you will see commented and explained come from the famous collection Mathematical Cuneiform texts. This is a selection, almost all from the OB period, and the selection was made according to a particular view of what was interesting. If you look at an account of Babylonian mathematics in almost any history book, what you see will have been filtered through the particular preoccupations of Neugebauer and his contemporaries, for whom OB mathematics was fascinating in part because it appeared both difficult and in some sense useless. The broader alternative views which have been mentioned do not often find their way into college histories. It should be added that Neugebauer and Sachs's book is itself long out of print, and almost no library stocks it. Your chances of seeing a copy are slim. Because the texts are so repetitive, the selections given in textbooks, in particular Fauvel and Gray, give a pretty good picture of OB mathematics as it was known 50 years ago. All the same, they are selections from a large body of texts. Other useful reading, again not necessarily accessible in most libraries, is to be found in the works of Hoyrup, Neeson et al. And Robson. There is a useful selection of internet material at Melville Mesomath, and in particular you can find various bibliographies, particularly the recent one by Robson. Exercise 1. Consider the example given above. Try to correlate the original text with the pictures and the translation. Can you find out anything about either the script or the meaning of the words in the original as a result? How much editing seems to have been done? And how comprehensible is the end product? Exercise 2. Clearly what we have here, in the translation, is a question and its answer. If I add the information that there are 60 jinn in 1 mana, what do you think the question is? And how would you get at the answer? 3. Discussion of the example. As is often observed, the problem above appears impractical until you look at it more closely. It was said, we are told, as an exercise in one of the schools of the Babylonian Empire where the caste known as scribes, who formed the bureaucracy, were trained in the skills they needed, literacy, numeracy, and their application to administration. The usual answer to exercise 2 is as follows. You have a stone of unknown weight. In our language, you would call the weight x jin. You then multiply the weight by 8 and add 3 jin, giving a weight of 8x plus 3. However, worse is yet to come. You now multiply 1/3 of 1/13 by 21. What this means is that you take the fraction 1321 is equal to 2139, and multiply that by the 8x plus 3. You are not told that, but the tablets explain no more than they have to, and the problem does not come right without it, so we have to assume that the language which may seem ambiguous to us was not so to the scribes. Adding this, we have 8x plus 3 plus 2139 is equal to 60. Here we have turned the mana into 60 jin. Clearly, as a way of weighing stones, this is preposterous, but perhaps it is not so very different from many equally artificial arithmetic problems which are set in schools, or were until recently. Effectively, and this is a point which we could deduce without much help from experts, although they concur in the view, such exercises were mental gymnastics more than training for a future career in stone weighing. An advantage of beginning with the Babylonians is that their writing gives us a strong sense of historical otherness. Even if we can understand what the question is aiming at, the way in which it is put and the steps which are filled in or omitted give us the sense of a different culture, asking and answering questions in a different way, although the answer may be in some sense the same. In this respect, such writing differs from that of the Greeks, who we often feel are speaking a similar language even when they are not. You are asked a question. The type of question points you to a procedure, which you can locate in a procedure text. To carry it out, you use calculations derived from a table text. These tell you how to multiply numbers, to divide, and to square them. As James Ritter says, the systematization of both procedure and table texts served as a means to the same end, that of providing a network or grill through which the mathematical world could be seized and understood, at least in an operational sense. It is worth noting that part of Ritter's aim in the text from which the above passage is taken is to situate the mathematical texts, in relation to other forms of procedure, from medicine to divination, in OB society. They all provide the practitioner with recipes of form, if you are confronted with. For this included not only their own language but a dead language, Sumerian, which carried higher status, as civil servants in England 100 years ago had to learn Latin. Problem A, then do procedure B. The point of the sum, then, is not mysterious, and indeed we can recognize in it some of our own school methods. First, scribes are trained to follow rules. Second, they are required to use them to do something difficult. As usual, such an ability marks them off as workers by brain rather than by hand, and fixes their relatively privileged place in the social order. We know something of the arduous training and the beatings that went with it, but not what happened to those trainees who failed to make the grade. What is mysterious in this particular case is the way in which one is supposed to get to the answer from the question, since the tablet gives no clue. Here the term a procedure text is rather a misnomer, but other tablets are more explicit on harder problems. With our knowledge of algebra, we can say that the equation above leads to 39 plus 2139 equals 60. And so, 8x plus 3 is equal to 39, and x equals 4. The fact that 39 and 21 add to 60, one would suppose, could not have escaped the setter of the problem, but language, such as I have just used, would have been quite impossible. What method would have been available? The Egyptians solved simple linear equations, such as 4 times plus 3 is equal to 87 by a false position, guessing a likely answer, finding it is wrong, and scaling to get the right one. This seems not to work easily in this case. To spend some time thinking about how the problem could have been solved is already an interesting introduction to the world of the OB mathematician. Having looked at just one example, let us broaden out to the general field of OB mathematics. What were its methods and procedures? What was distinctive about it? And second, do the terms. Elementary and advanced make sense in the context of what the Babylonians were trying to do, and if so, which is appropriate? For the importance of number writing. As we have already pointed out, Neugebauer and his generation were working on a restricted range of material. To some extent this was an advantage, in that it had some coherence, but even so, there were typical problems in determining provenance and date, because they were processing the badly stored finds of many earlier archaeologists, who had taken no trouble to read what they had brought back. It is well worth reading the whole of Neugebauer's chapter on sources, which contains a long diatribe on the priorities and practices of museums, archaeological funds, and scholars. Only minute fractions of the holdings of collections are catalogued. And several of the few existing rudimentary catalogues are carefully secluded from any outside use. I would be surprised if a tenth of all tablets in museums have ever been identified in any kind of catalogue. The task of excavating the source material in museums is of much greater urgency than the accumulation of new uncounted thousands of texts on top of the never investigated previous thousands. I have no official records of expenditures for expeditions at my disposal, but figures mentioned in the press show that a preliminary excavation in one season costs about as much as the salary of an Assyriologist, for 12 to 15 years. And the result of every such dig is frequently more tablets than can be handled by one scholar in 15 years. There is probably better conservation of tablets now than when the above was written, but the long delay in publishing is still a problem, and there are grounds for new pessimism now that one hears that tablets are being removed from sites in Iraq and traded, presumably with no provenance or indication of place and date, over the internet. For a discussion by Eleanor Robson of these and other problems which face historians in the aftermath of the Iraq War, see. The best known of the OB tablets can be seen as rather special. What can be recognized in them are several features that subsequent scholars felt could be identified as truly mathematical. 1. The use of a sophisticated system for writing numbers. 2. The ability to deal with quadratic equations. 3. The uselessness of problems, even if they were framed in an apparently useful language, like the one above. None of these characteristics are present in the mathematics of the immediately preceding period, which in itself is noteworthy. Let us consider them in more detail. The number system. You will find this described, usually with admiration, in numerous textbooks. The essence was as follows. Today we write our numbers in a place values system, derived from India, using the symbols 0, 1, 9, so that the figure 3 appearing in a number means 3, 30, 300, etc., depending on where it is placed. The Babylonians used a similar system, but the base was 60 instead of 10, and they therefore based it on signs corresponding to the numbers 1, 59, without a zeros sign. The signs were made by combining symbols for a 10 and a 1, a relic of an earlier mixed system, but obviously practical, in that what was needed was some easily comprehensible system of 59 signs. You might, as an exercise, think of how to design one. The place value system was constructed, like ours, by setting these basic signs side by side. We usually transliterate them and add commas, so that they can be read as in Fig. 5, 1, 40 means, then, what we would call 160 plus 40 is equal to 100, 2, 30, 30, means 260 plus 30, 60 plus 30 is equal to 7,200 plus 1,800 plus 30 is equal to 9,030. 60 plays the role which 10 plays in our system. There are, though, important differences from our practice. First, it is not explicitly clear that 30 on its own, with no further numbers involved, necessarily means what we should call 30. It may mean 30-60 or 30-60. In a problem, it will be 30-somethings, a measurement of some kind, which is stated explicitly, for example, length or area in appropriate units, and this will usually make clear which meaning it should have. This is not the case with table texts, which often concern simple numbers. Furthermore, compare our decimals. 30 can also mean 3160 is equal to 12, and often does 0.7 or 30,160,160 and so on. If the answer was written as 30, you should, and this is an idea which we can recognize from our own practice, be able to deduce what 30 meant from the context. 6. Robson cites an example of a collection of proverb texts which were published in 1960 with no acknowledgement by the scholarly editor that they had calculations on the back. 7. Although there were also symbols for the commonest fractions like, see the above example, and rules about when you used them. Figure 4. The basic cuneiform numbers from 1 to 60. Figure 5. How larger cuneiform numbers are formed. You can find the details of how the system works in various textbooks. In particular, there are plenty of examples in Fauvel and Gray. Again, following a general convention, modern editors make things easier for readers by inserting a semicolon where they deduce that the decimal point must have come, and inserting zeros as in 30, 0, or 0, 30. So a 1, 20 means 80, but a 1, 20 means 1 plus 20, 60 is equal to 1. There would be no distinction in a Babylonian text, both would appear as 120. To help themselves, the Babylonians, as we do, needed to learn their tables. They were, it would seem, in a worse situation than us, since there were in principle 59 tables to learn, but they probably used shortcuts. A scribe on site would quite possibly have carried tablets with the important multiplication tables on them, as an engineer or accountant today will carry a pocket calculator or palm top, and in particular the vital table of reciprocals. This lists, for a numbers x, the value of the reciprocal, and starts. 2. 33. 24. 15 5. 12 6. 10 7, 30. 8 8. 7, 39. 6, 40. Using this table, it is possible to divide simply by multiplying by the reciprocal. Dividing by 4 is multiplying by 15. This way of writing numbers is so advanced and sophisticated that it has impressed most commentators, particularly mathematicians. The absence of a decimal point, as I have said, is not a serious problem in practical calculations, but it could raise questions when one is asked, for example, to take the square root of 15. If 15 means, then it has square root 30 equals, but if it means 15, of course, it does not have an exact square root. However, the scribe would find the square root by looking in a table, and only one answer would appear, for any number. The more serious problem which is often pointed out is the absence of a sign for 0. In principle, 60, which should in our terms be 1030, would be written 130, which could also mean 90. It is hard to know how often this caused confusion. One case is given by Damerow and England of a scribe who is finding the powers of a 140, or what we would call 100. At the 6th stage, one of the figures should be at a 0, and is omitted. Hence this calculation, and the subsequent ones are wrong. However, you can see that this mistake would occur less often than in our decimal system if we happen to forget zeros, and so confused 105 and 15. Exercise 3. Explain how the table of reciprocals works, why it does not contain 7. Exercise 4. Work out using the table, given that the reciprocal of 8 is 7, 30. Exercise 5. What is the square root of 15 if 15 means 1560? Show that, in Babylonian terms, there cannot be two different interpretations of a number which have different square roots. 5. Abstraction and uselessness. The discovery of the sexagesimal system is sometimes described, by those who like the word, as a revolution. How it came about is unclear, but it does seem to have arisen quite suddenly out of a number of near or pseudo-sexagesimal systems, around the beginning of the OB period. Damerow and England seem to consider it impractical and claim it did not outlast the OB period, which is difficult to reconcile with their admission that it was used by the Greek astronomers. Here, indeed, we find our first example of the problem of connecting similar practices across time. Sexagesimals were used in Babylon in 1800 BCE, and again, mainly in astronomy, 1,500 years later, under the name astronomers' numbers. It seems almost certain that this was a direct line of descent from Babylon to Greece. More dubious claims are often made, though, in situations where the same result is known to two different societies, that there must have been either communication or a common ancestor. Such arguments are central to van der Waerden's fascinating but eccentric. Always controversial, they have to be evaluated on the basis of the evidence. Equations. Here, if anywhere, the mathematicians can be allowed to judge what it is to be sophisticated. In examples like the one above, we see probably for the first time the idea of an unknown quantity, an unweighed stone, in this case. The Egyptians were using the same idea a little afterwards, and may have arrived at it independently, but they did not succeed in the next step, which was a general method for solving quadratic-type problems. It makes sense to use this term rather than quadratic equations, since the problems are very varied in nature. The quadratic equation, as we know it, a combination of squares, things, and constants, begins its history properly in the Islamic period. Fauvel and Gray's 1-e, problem 7 starts. I have added up 7 times the side of my square and 11 times the area, 6, 15. In other words, we have a square, and we are told that 7 times the unknown side x added to 11 times the area gives 6, 15 or 6. This leads to a simple quadratic equation, which we would write 7x plus 11x equals 6, with answer x equals 0, 30 equals. For how it is solved, which in particular shows where square roots were used, see Appendix A. In addition to the relatively common equation texts, we have some texts which seem to show extra mathematical sophistication, some of which is still subject to debate. One is the notorious Plimpton 322, for the original decoding of this see Fauvel and Gray, and for a recent counter-argument, Robson. We shall not consider this here, although it is an interesting introduction to the disagreements of historians. A simpler case is the square root of 2 tablet, which seems straightforward in its interpretation. The picture shows a square, its side is marked 30. And the diagonal has 2 sexagesimal numbers marked. One is a good approximation to 2. The other to the diagonal 2, 2. Nearly the same sexagesimal numbers will appear again when we deal with Islamic mathematicians over 3,000 years later. For now it is worth raising the question of what these numbers were used for, and how they were arrived at. In the absence of any written procedures, we can at least admire the result. Uselessness. Sometimes mathematicians need to be reminded that mathematics, to be worthwhile, does not have to be useless, and they have often had a two-faced attitude on the subject, pointing e.g. when Figure 6 the square root of 2, tablet YBC 7289. Requesting a research grant to results which were thought useless at the time and afterwards discovered to have an application. Well-known examples include Riemannian geometry and relativity, finite fields and the manufacture of CDs, etc. It has been a part of the case for the seriousness of Babylonian mathematics that their problems, while apparently practical, were clearly not designed for their real world. Rather, they were exercises in technique adressée d'une pratique language. The point is often made, and can hardly be contested. Our first example is a good illustration. So is the quadratic equation above. It would be hard to think of circumstances in which one would want to add lengths to areas, and the Greeks, with a more strict idea of geometry, did not have a language in which to do it. In another example often cited, the student is given the amount of earth required to fill a ramp, and asked to find its dimensions, exactly the opposite of the practical question. No Babylonian text theorizes this impracticality as such, or makes a virtue of it, while Plato, as we shall see, makes a distinction between real mathematics and that which is used by artisans. The Babylonian scribes to all appearances were trained for a career of useful tasks by solving problems with no application. What was the point of this? To answer this question would require some thought about what the point of any mathematical procedure is. At one level, we can imagine that the ability to deal with increasingly difficult problems, regardless of their meaning, could be used as an examination-type filtering mechanism within the scribal schools, marking off the bright students from the mediocre ones, or outside the schools. It could be a form of competition between freelance scribes who are trying to attract clients. This virtuosity is part of a whole package of skills which were important for self-definition and for status. According to the examination texta, the accomplished scribe must know everything about bilingual texts. He must know occult writings, and occult meanings of signs in Akkadian as well as Sumerian. He must be familiar with the concepts of musical practice. And he must understand the distorted idiom of various crafts and trades. Into the bargain then comes mathematics. All that has a totality, has a name, namluulu, humanity. This external explanation does not, however, account for the particular choice of impractical quadratic equations for the display of accomplishment. Here we have, almost, an example of Kuhn's normal science. A technique, the solution of linear and quadratic problems using sexagesimal numbers and tables, becomes available, for reasons which are unclear, and the scholars who make up the community are defined by their ability to solve puzzles using the technique. In addition, they may find the problems interesting or challenging in a career dedicated to routine tasks. In principle, hard puzzles can generate harder ones without limit. In terms of the historical record, it seems that either invasion or loss of interest or both put an end to the practice. The idea of a uselessness is one which needs to be treated with some care, however. It is easy, considering some of the OB calculations, to deduce that their apparent practicality is a fake and that they are simply occasions for what Heurup calls displays of scribal virtuosity. This is the traditional view, and many of the texts support it. However, Robson's detailed new publication, containing a wide variety of tablets, is the basis for arguing a more complex view. An example is a long tablet containing a succession of problems about brick walls. These depend crucially for their solution on one of the basic scribe's numbers, the conversion factors from to and back, an eminently practical figure, and one which was certainly often used. The problems start with questions which give the measurements of the wall and ask how many bricks. Naturally, the OB scribes used different units for width and length and height. The calculation was therefore not always a straightforward one leading to a certain number of cubic nindan, and dividing by the number of bricks in a cubic nindan. Such a question seems both simple and practical, and just the kind of thing which a scribe in the brickwall construction trade might be asked. However, question 5 on the same tablet is a wall. The height is 1 nindan, the bricks 45 sar. The length exceeds the width of the wall by 20 nindan. What are the length and the width of my wall? The details of brick measure and height belong to everyday practice, but it seems very unlikely that one would ever need to answer a question of this type in a practical situation. Somewhere along the list of problems on the tablet a link to real-world wall building has been broken. Exercise 6. If you are told that 72 sar of bricks occupy a volume of 1 cubic nindan, show that this is equivalent to a quadratic problem and find the answer. 6. What went before? The last example shows that there may still be more to learn about the OB period. In recent times, a much fuller picture has emerged of the earlier period of mathematics, and it is currently perhaps the most interesting area of research. What we have is still more a series of snapshots than a record of discovery. In archaeology, it is almost unknown to find an innovation which can be accounted for, much less attributed to an author, but it allows us to question the idea of Babylonian mathematics as the earliest serious practice, based on the criteria I have given. In the first place, we know that the profession of scribe, and the scribal schools, existed for some time before. Even in this very early period, when the number system, while quite clear and flexible, was much less advanced than the sexagesimal one, we find that the schools had discovered the idea of setting problems which were both difficult and useless, if in a different way. In fact, the mixed nature of the number system made questions which we might think easy harder. They require simple division of a very large number by a number which makes problems. Specifically, that the content of a silo containing 2,400 greatger, each of 480 sila, be distributed in rations of 7 sila per man. A sila being roughly a liter, we are dealing with over 1 million liters, and the proposed division by 7 is an exercise in obsessive accuracy rather than a practical problem. In the words of Joran Freeberg, The obvious implication is that the current fashion among mathematicians about 4.5 millennia ago was to study non-trivial division problems involving large numbers and non-regular divisors such as 7 and 33. Freeberg uses the term mathematicians to describe those scribes and teachers who discussed such problems, and such a usage not only sets the origin of mathematics as an independent practice much earlier, but makes it appear much more trivial to us. If the Babylonians can begrudgingly admired for solving quadratic equations, can we extend a similar recognition to the scribes of Farah for doing rather long divisions? There has indeed been quite a controversy about what the Farah scribes were supposed to do in answering the question. See Powell in Fauvel and Gray 1. E.5, or for a more recent view, Melville, Ration computations at Farah, multiplication or repeated addition, in Steele and Imhausen. Again, this question is perhaps best left unanswered, or as a point for discussion. Freeberg would probably justify calling the scribes mathematicians, not in terms of their use of unrealistic examples, but in the formation of a community, again that Cuneian word, with a common project, whose language was a language of numbers. Training for practical purposes seems, here too, to have generated a class of impractical exercises, if entirely different from those which followed 500 years later. However, this impracticality, characteristic of the school texts which have survived, disappears when we look at a different family of texts, the accounts from the harsh period known as UR3, which were the work of practicing scribes and administrators. Dating from the 21st century BCE, these are in time between the Farah texts and the OB ones, and they are both utilitarian and highly mathematized. The period, under King Solji, was one of increasingly rigid centralized control of production, the aim, for a variety of industries, seed production, cattle raising, fishing, milling, and so on, is to calculate the expected yield and the extent to which the farmers or managers fulfill their targets. Analogies with old Soviet planning or indeed modern Western management come to mind. Accounts were complicated by the fact that almost any quantity had a special system of units to measure it. However, the scribe is, on the whole, up to the calculation. As usual, there are tables of conversion factors to help. Here is an example which, according to Damerow and England, represents the calculation of the harvest yield of the province of Lagash for the third year recorded in the text. We begin. Figure 7, the tablet recording harvests from Lagash, AO 3448. By setting out the area. 1111 field surface. Then follow the targets, the amount which this area should produce, the barley involved, 3533 gur finally, the actual amount produced, and the shortfall, therefrom. 21474 214 gur delivered. Deficit, 1343273 gur. A first observation is that a quite unnecessary number of units of measurement seem to be involved. They are of course exotic to us, but at 4,000 years distance we can expect that. The first row gives the area of the fields producing barley. According to Neeson et al. 1993, pp 141, 1 bur is about 6.3 hectares, and 1 sar equals 60 bur 1 saru equals 10 sar 1 sar gal equals 6 saru. The total area is therefore 4261 bur, or 26,844 hectares. The calculation of the barley involved in the second row is the target. It assumes that an area of 1 bur produces 30 gur of grain. For the grain measure we have 1 barig equals 6 ban 1 gur equals 5 barig 1 u equals 10 gur 1 guess equals 6 u 1 guess u equals 10 guess 1 sar equals 6 guess u 1 sar u equals 10 sar. As you can see, the units do not proceed by uniform steps, and even multiplying the area by the factor of 30 gur and translating it into volume units to get the target volume is quite complicated. Hence the figures 1 and 1 and 1 in the first row translate into 3, 5, 3, 3 in the second. We now have to subtract the actual output from the target, and the actual figure involves a rather excessive 8 units of measurement. This should be enough to convince you that, while UR3 accountants' arithmetic was elementary, it was far from simple, and considerable skill was required to get the deficit right. The targets set for laborers in factories seem generally to have been unrealistically high and calculated. 8. But before we condemn the Sumerians for their complexity, it should be noted that schools in England 50 years ago taught a system of 8 units of length, line, inch, foot, yard, rod, chain, furlong, mile, and that the factors relating them were more complicated than the Sumerian fives, SAXS, and tens. To ruin their overseers to the greater profit of the state. Of course, we still sometimes face problems of this multi-unit kind, such as when we try to find the time-lapse between 1:25 p.m. on January 28th and 11:15 a.m. on February 2nd in days, hours, and minutes, but these are rare and the metric system is reducing them. Exercise 7. Trace the calculation of the barley involved through and check it. Exercise 8. Calculate the deficit, using the table of barley measures, and find the 2 places where the scribe has made a mistake. 7. Some conclusions. The above example is worth some consideration, if only because you will not often find such work discussed. In a sense the mathematics is trivial, in another clearly not, it is highly organized, and it needs to be accurate. It is as much a product of the bureaucracy and the organization of scribes as are the more interesting and mathematically impressive OB examples with which we started, and which you will usually meet, and its basic tools, multiplication and subtraction, with the conversion factors to make it more difficult, have also had a long history, and are still with us. The rationality of the OB system is often mentioned to boost its credentials as the earliest real mathematics, as is the fact that it survives in our measurements of time and angle. However, even today we often in practice find we have to operate with mixed systems of measurement, and work out the relevant sums as best we can. We could call such a procedure irrational, it does not make the mathematics easier. Only those who have never made mistakes in such conversions can dismiss them as not mathematical. Appendix A. A solution of the quadratic problem. The solution given, problem 7, is as follows. The intrusive semicolons have been omitted, you will have to work out where they should come. On the other hand, the procedure is translated into algebraic notation in brackets, so that it can be followed more easily. You write down 7 and 11. You multiply 6, 15 by 11, 1, 8, 45. You break off half of 7. You multiply 3, 30 and 3, 30. You add 12, 15 to 1, 8, 45. Result 1, 21. Plus AC, if the equation is ax plus bx equals c. This is the square of 9. You subtract 3, 30, which you multiplied, from 9. Result 5, 30. Plus AC, in the usual formula, we now have to divide this by a equals 11, which we proceed to do. The reciprocal of 11 cannot be found. By what must I multiply 11 to obtain 530? The side of the square is 30. Solutions to exercises. 1. I shall not answer, while exercise 2 is answered in the text. 3. If the number in the left column is x, that in the right column is y where x, y equals 1. How does this work? For example, 4. 15 is equal to 60, and 8 is equal to 8. 7 plus 8 is equal to 56 plus 4 is equal to 60 again. More generally, one could think of x and y as solving some equation x. Y equals 60, the value of k is immaterial, since in Babylonian notation we cannot, for example, tell the different answers 15 and 0, 15 apart. This process works if such a y can be found, that is, if x divides some power of 60 exactly. This will be true if all the factors of x are 2s, 3s, and 5s. It will therefore not work for 7. 4 would be calculated as 1, 47, 30. Use the formulae, 740 is equal to 4, 40 and 30 40 is equal to 20, 0, and take care of place value. You find the product is 7, 0, 0 plus 4, 40, 0 plus 30, 0 plus 20, 0 is equal to 12, 30, 0. If you were a Babylonian scribe, and knew that the 1, 40 meant 100, you would have no difficulty in interpreting this answer as 12. 5, 1. Of course, 1560 is equal to 900, which is a square, indeed the square of 30. So the statement, square root of 15 is 30, is true also for this interpretation of 15. 2. This is a standard fact about place value systems. The different interpretations of any number are, say, a basic x, and x60. If x equals y, then x60 is a square if and only if k is even, say k equals 2l, when x60 is the square of y60. So, in Babylonian terms, the square root of x is always y. 6. The Babylonian answer is given in Robson. It is hard to follow, since the text switches between the sar, nindan, and cubits. Above, we have given the conversion factor from bricks to volume in cubic nindan instead of sar to reduce the number of measures. Here is a simplified version of the answer in our notation. 45 sar of bricks occupy 1524 cubic nindan, so that is the volume. The height is 1, so the area is 12 square nindan. If L is the length and W the width, L equals W plus, and LW equals 12, so WW plus 7,3 equals 512. 12W plus 28W equals 5. Clearly this is quadratic, and the solutions are W equals and W equals realistically. The wall has width nindan and length 2 nindan. 7. We could, as above, reduce everything to the simplest units, but that is probably not what was done. To proceed properly, start from the right. 1 ber gives 30 ger or 3u from the table. 1 sar therefore gives 63u, or 3 guess u. 1 sar u gives 10 times this, which is 30 guess u, or 5 sar. And finally, 1 sar gal gives 6 times this, which is 30 sar, or 3 sar u. 32. A History of Mathematics 8. We now have to subtract. This time again, it is more correct to borrow along the line. However, since you can risk making mistakes quite easily given the number of zeros in the top row, I will reduce everything to ban. The amount due is 3,834,900 ban. The amount delivered is 2,353,870 ban. And the deficit is 1,481,030 ban, which is 1,080,000 plus 3. 240,000 equals 3,108,000 plus 72,000 equals 418,000 plus 3,600 is equal to 2,1800. Plus 1,200 is equal to 4,300 plus 210 is equal to 730 plus 18 is equal to 36 plus 2 ban. This agrees with the scribe's calculation apart from the figures for you and guess. 2 Greeks and origins. Socrates. Then as between the calculating and measurement employed in building or commerce and the geometry and calculation employed in philosophy. Well, should we say there is one sort of each, or should we recognize 2 sorts? Protarchus, on the strength of what has been said, I should give my vote for there being 2. 1 Plato and the Meno. One feature of mathematics which has remained fairly constant from the earliest times to the present day is a general view that its aim is to use numbers to solve problems which arise in the world. However, another idea has been widespread among mathematicians at least since the time of the ancient Greeks, and its statement dates back to Plato, whose different view is summarized above. There is a down-to-earth mathematics which you use for accounts and measuring, and there is a superior mathematics which I use for some other purpose. What we know of this view, what its implications were, and its early history are the subject of this chapter. Plato, a philosopher, whose dates are usually given as roughly 427, 348 BCE, and who was mostly writing in the early 4th century, is one of the central figures in the history of Greek mathematics. There are a number of reasons for this. A simple one is that Plato dealt in some detail with mathematical questions in his works, and, while mathematics had supposedly been practiced for 200 years before his time, his dialogues are the earliest first-hand documents which we have. Almost equally important is that, as the quotation indicates, Plato defined a particular view of what mathematics was, or should be. A rough characterization is that real mathematics is more abstract. Numbers are no longer numbers of the things, or measurements of length, area, or time, but have an independent existence as objects which you reason with. As Socrates says earlier in the same dialogue, the ordinary arithmetician, surely, operates with unequal units. His two may be two armies or two cows or two anythings from the smallest thing in the world to the biggest, while the philosopher will have nothing to do with him, unless he consents to make every single instance of his unit equal to every other of its infinite number of instances. And while not all of his successors agreed with this approach, those who did were those who had most influence. This is especially true of some very late writers, who are the main authorities for what we know of the history. One of Plato's longest and clearest mathematical discussions, often referred to, is in the dialogue called the Meno. Fowler has text with variations of his own construction, and the whole dialogue is online, for example. Figure 1. The Meno argument. The large square has side 4 feet, the 4 small squares have side 2 feet. The 4 diagonals form a square of area 8 square feet. At Plato Meno.html. What is done in this dialogue is a good introduction to Greek mathematics, or the kind which is considered atypical, the classics if you like. The other kinds, referred to in our opening quotation, will be discussed in the next chapter. Although the problem and the solution would easily have been available to the Egyptians or Babylonians 1,000 years earlier, what seems suddenly to be new is the appeal to argument and discussion. The philosophical point of the dialogue is an idea about a knowing. Socrates has a strange theory that the truths which we know have not been learned but were always present in our minds, and we simply bring them to consciousness or remember them. With this aim, he calls over a supposedly ignorant slave boy and asks him how, if you are given a square of side 2 feet, you can construct a square twice the size. Since the original square has an area of 4 square feet, then the one you construct must have an area of 8. The slave boy suggests squares of side 4 feet and 3 feet. He then becomes perplexed and admits to not knowing. Socrates then, we assume, draws the figure shown and continues to find out from the boy that it contains the answer to the problem. His arguments are given in Appendix A to this chapter and are conceptually quite simple. 1. Each of the 4 squares in the diagram is 2 square feet, and so has an area 4 square feet. 2. So each of the 8 triangles has an area of 2 square feet. 3. Now look at the square made by the 4 diagonals. It consists of 4 triangles, so its area must be 4, 2, or 8 square feet. 4. It is therefore twice the area of the square we started off with, so it is the square of double the size we were looking for. It is easy to find fault with the way the dialogue is conducted. Socrates is in fact leading the witness inadmissibly, putting the answer which he himself knows into the boy's mouth, and then claiming that he has done nothing of the kind. However, more purely mathematical objections arise, and they relate to some key ideas about the nature of Greek mathematics. In particular, a question which Socrates does not deal with, which is interesting given the precise use of numbers like 2 feet, 3 feet, and so on, is what the length of the diagonal is. Today, we would say that, since the area is 8, the side must be 8 is equal to 2.828, which is not a whole number, or even an irrational number. You can approximate it as closely as you like by fractions, but the result will never be exact. As Michel Serres points out, in a detailed discussion of the dialogue, nobody asks the asker, how long? He questions the ignorant slave about a content about which nobody, however, bothers him. He found the side all right, but he did not measure it. Socrates is cheating. He knows that he will not find the exact length. In fact, one reason why this particular problem has been chosen for the dialogue is perhaps, but here, as usual, we have to start attributing motives to the Greeks, because it shows the limitations of numbers, and the superior power of geometrical methods. The boy will never arrive at the right answer by guessing different numbers, but Socrates can draw a picture which solves it. The philosopher's mathematics not only uses a more abstract idea of a number, but when number becomes a problem, it can dispense with it. Greeks said that ratios such as diagonal to side were talagoi, without a reason, irrational. More simply, they said that the side and the diagonal were incommensurable, that is, There is no shorter line L having the property that both side and diagonal are exact multiples of L. We shall return to these terms, and the problems they pose, later. Exercise 1. Is it obvious that the figure which Socrates constructs in Figure 1 is a square? Why? Exercise 2. Why does diagonal is incommensurable with side I mean the same to us as 2 is not a fraction? Exercise 3. Why is 2 not a fraction anyway? 2 Literature. It is striking that near the end of the 20th century there should appear 2 books arguing that much of the history of Greek mathematics, written during that century, is wrong. RevealNets argues that it is wrong because historians have not understood the crucial roles that language and diagrams played in shaping the deductive structure that is Greek mathematics' most striking characteristic. David Fowler argues that it is wrong because a key component of the mathematics that developed in and around Plato's Academy was lost in Hellenistic times and was not rediscovered until the Renaissance. The literature on ancient Greek mathematics, as the above quotation reminds us, is large and in constant flux. We shall consider the specific problem of the ancient Greek texts themselves shortly. For the moment, let us concentrate on what material is available on the period, as primary and secondary sources. The standard reference text is certainly Heath's, a reprint of a 1921 classic. Because it is so old, and so much a standard work, it is the basis for most later authors' arguments, disagreements, and conjectural reconstructions. The main primary sources for the period we are considering, up to and including Euclid, around 300 BC, are the works of Plato, Aristotle, and Euclid himself. Fauvel and Gray give plentiful extracts from all of them, and all can be found easily on the internet. It is very strongly recommended that you read some of these texts, which vary from 1. There is evidence that Plato did know that the side of the 8-foot square was not a rational number, from the Theaetetus. See extract in Fauvel and Gray 2.3, pp 73, for but the question is not raised in the Meno. Why not? Quite easy to spectacularly difficult. This will give some idea of the achievements of Greek mathematics, of its range, and of the limits within which it operated. In Fauvel and Gray you will also find some useful extracts from the very late commentator Proclus, for whom see later. With regard to secondary literature, the situation is better, since the question of the earliest Greeks, their aims, and achievements, has seemed so important. We will discuss why later. There are sections on the Greeks in both van der Waerden and Neugebauer. They are sometimes dated, and in van der Waerden's case, given to conjecture using unreliable ancient sources. The major modern works which cover the question can be dauntingly detailed, but if you find yourself developing, as one does, an interest in Greek mathematics, they will draw you in. The central works are probably Knorr's attempt to account for the form of the elements and Fowler's more informal, but very scholarly reconstruction of what geometry might have been like before Euclid. Nets gives an intriguingly different approach, by a consideration of actual Greek proofs and how they work, followed by a sociology of Greek mathematicians based on the very fragmentary evidence we have about them. We shall refer to other texts when they are useful, but these will do for the present. You have a reasonable chance, given the prestige of Greek mathematics, of finding some or all of them in your library. 3. An example. Being in a gentleman's library, Euclid's Elements lay open, and it was the 47 L Librae he. Read the proposition. By G, said he, this is impossible. So he reads the demonstration of it, which referred him back to such a proposition, which proposition he read. That referred him back to another, which he also read. Et sic inceps that at last he was demonstratively convinced of that truth. This made him in love with geometry. While the Meno is a very illuminating discussion on a mathematical subject, it is too informal to be a good illustration of the mainstream Greek mathematics, which is our primary concern. Socrates' arguments make no attempt to go back to first principles, and the points he makes about areas of triangles are treated as obvious rather than justified in painful detail. The mathematical argument of the Meno, if not its philosophical one, would have been easily accessible to an Egyptian. To see how classical Greek mathematics claims to work, it is best to start, at least, with Euclid's Elements. This is a strange and complex work, some would say a composite, or scissors and paste compilation of previous works, but it has been the most read and commented of all mathematical works in history, so it deserves a central position in any account. For that reason, we shall privilege it over the harder works of Archimedes and Apollonius, the other main classics. It is also a sensible idea in the first place to consider it in itself as a text rather than speculating on its origins. Such speculation is natural in a history which focuses on discovery, but other histories are available. A whole book could be written about the elements, and many have. The most recent and scholarly are Knorr and Artmann. The work, as its title suggests, is supposed to give the student the essentials of mathematics, carefully deduced from first principles, statements which are either in some sense obvious, or which the reader-student can reasonably allow to be true. Here, as Figure 2, the diagram for Euclid proposition I.35. An example of the approach is a single short proposition. The aim is a simple one, to show that two parallelograms with the same base and the same height have equal area. In Euclid's language, they are just called equal. Proposition I.35. Parallelograms which are on the same base and in the same parallels equal one another. Let ABCD and EBCF be parallelograms on the same base BC and in the same parallels AF and BC. I say that ABCD equals the parallelogram EBCF. Since ABCD is a parallelogram, therefore AD equals BC. For the same reason EF equals BC, so that AD also equals EF. And DE is common, therefore the whole AE equals the whole DF. But AB also equals DC, therefore, the two sides EA and AB equal the two sides FD and DC, respectively, and the angle FDC equals the angle EAB, the exterior equals the interior. Therefore, the base EB equals the base FC, and the triangle EAB equals the triangle FDC. Subtract DGE from each. Then the trapezium ABGD, which remains, equals the trapezium EGCF. Add the triangle GBC to each. Then the whole parallelogram ABCD equals the whole parallelogram EBCF. Therefore, parallelograms which are on the same base and in the same parallels equal one another. QED. This result stands instead of the numerical formula which we, like the ancient Egyptians and Babylonians, would use to relate the area of a parallelogram to the length of the base and to the height. This use of the term equal, to mean having the same area, is not in Euclid's list of definitions. You are supposed to know what it means. Here we see it as retrospectively defined by adding and subtracting the triangles DGE and GBC, starting from two triangles which themselves are equal in all respects, all sides and all angles correspond. So, equal means having equal area, but paradoxically, area is undefined. In a sense, the process is a sleight of hand. Notice also that the point G is not defined, except by the diagram, and also, that the proof as stated only works if G is as shown, that is, if CD crosses B between the parallels. You can adjust the proof for the case where it does not. Is this a mistake? Such minor oversights do occur, and have worried commentators, but they are not, perhaps you will agree, very important unless you suppose the elements to be perfect. As you see, and this is Euclid's most famous and influential characteristic, every statement is backed up by a reference back to a previous result, or in this case to a common notion. For example, common notion 1, clearly important in the proof, states that if equals are added to equals, the results will be equal. This deductive structure is still in use today. It has been usual to treat Greek mathematics as part of our Western tradition, and so is similar to our own, and indeed the style of exposition and the material are familiar, but the actual aim of the proposition is unusual from our viewpoint, as it would have been for the Egyptians. It tells us only that two parallelograms have equal areas, instead of saying what those areas are. Does this mean that Euclid did not think of areas as numbers? There is evidence that he did not. To do so, you have to have a fixed unit of measure, and this the Elements is unwilling to do. In fact, the Elements is not a user-friendly text. To put it mildly, there are no examples, no explanations of aims and objectives, or of the uses to which any result can be put. All this the reader has to invent. And, because Euclid did not explain his aim, we have to use other sources to try and find out what he was trying to do and why. Here are 2 other examples of the thinking in the Elements to illustrate what I mean. 1. Today, we usually think of Pythagoras' theorem as a statement about numbers. Again, this theorem was known in much the same sense by the Egyptians and Babylonians. In these terms, the theorem says that if a right-angled triangle has short sides of lengths A and B, and long side C, then A plus B equals C. But the theorem as stated in Euclid I.47 is about actual squares. If you draw the squares on the 3 sides, then you can cut up the squares on the 2 short sides and piece